Okay. So, today's topic is another very important topic. Ideal filter. Under this, actually we will come across a topic which is the main focus. It is called linear phase systems. But before I tell you what is linear phase system, suppose you have got one input sequence x n and it has got a discrete time Fourier transform this. So, this may be within a band, maybe something like this within some band, outside the band up to pi and minus pi. There may be unwanted signals here, unwanted say noise and all that. So, you want to filter it out. So, if you want to filter it out, and this is I am writing x e to the power j omega, but here it is very important to recall that you cannot plot a DTFT just like that. You can plot a magnitude, which is actually this case, and you have to have a separate phase plot. Okay, like this should actually be magnitude, and there will be another phase plot. Earlier I used to mention this, but I used to carry on with one plot because that was okay for explaining my point. But in this case, we have to make use of this fact that actual plot of the DTFT means magnitude versus frequency plot, and phase, that is angle. Angle could be anything, Suppose angle is like this, from minus pi to pi. Okay. That means, at any frequency, suppose at this frequency, height magnitude is say a and angle is say theta at the same frequency, okay. Then suppose the frequency is some omega naught, same omega naught. That means, at omega naught the DTFT, that is x e to the j omega naught, will be magnitude a times e to the power this j theta. This is the meaning of this. This is how to connect these two to get the actual DTFT. So, suppose this is given to you, but nevertheless this is band limited within some band. Outside the band there may be a unknown, there may be unwanted components, noise and all. So, you have to filter it. Filter means you want to pass this signal as it is without any distortion and remove all components which are outside this band. Okay. So, then filter magnitude response, then what should be the filter? Firstly, from here to here, say omega c to minus omega c, its magnitude should be constant. Okay. Normally, instead of showing magnitude, we write full thing DTFT, and that is constant, but what will happen to the phase then? Okay. That time we normally assume phase to be 0. So, e to the power 0, e to the power j 0 is 1. So, but why should the phase be 0? Because when you design a filter, you cannot guarantee that phase will be 0. Okay. There will be phase as a function of omega. So, what should be the phase? Magnitude should be constant, so that mod x e to the power j omega into mod h e to the power j omega will be just capital A times this shape. This shape will remain intact. Capital A can be chosen to be 1 also. But how about the phase? Because this is what this is, x e to the power j omega is mod into e to the power angle. Same for h. H e to the power j omega is magnitude at any point times the corresponding angle. Sorry, this is x, very sorry, this is x. So, when you multiply, when you pass a signal through the filter of transfer function h e to the power j omega, output will be product of the two DTFT. So, output magnitude will be mod of x e to the power j omega into mod of h e to the power j omega, and phase e to the power these two phases will add. So, summation phase will be added and magnitudes will be multiplied. Magnitude response is constant. So, mod x e to the power j omega into a within this band. So, it will be a times this. So, shape will be constant, shape will not change. Phase, question is what is the phase? Our claim is this angle for perfect reconstruction, that is for output to be same as input, maybe with a delay, but otherwise same as input. Our claim is that it is not enough for the magnitude only to be constant within this band. You have to tell about the phase. So, the phase, the claim that this should be just a constant multiple k times omega, a straight line. That is, maybe I can draw on this side, because this is magnitude, phase. If I plot versus omega, it should be some k omega. If k is positive, slope will be positive, k is negative, slope will be negative, like this. This is the claim. If phase is also like this, then our claim is that output of the filter will be same as the input of the filter, that is x n. Maybe x n will be delayed somewhat, but that delay is okay. Delay is known, delay does not change the shape of the waveform, right. This is our claim, we will easily verify it. Okay. But one thing remember, if k is 0, then phase is 0. That is what we often do, that is, we just show h to the power j omega, we do not take mod, and by that we assume that we are considering the special case of 0 phase, but actually why should the phase be 0? Okay. That is why in this case we are considering phase in a more general case, and we are saying that your digital filter should have not only magnitude response flat within the band, but its phase also should be linear in omega. It is a linear function k times omega, straight line going through origin. Okay. Why? Now, you can easily see here your x n, here is your transfer function h this, and here is your output y n. So, output y n will be what? Inverse transform of output DTFT. What is output DTFT? Product of the two DTFTs. Product of the two DTFTs, output DTFT, and then you power j omega n, d omega n is coming from here, your choice. This is the formula. We have seen it earlier also. The two DTFTs are multiplied, that is output DTFT, that times e to the power j omega n d omega minus pi to pi. And now, if you carry out this product, it will be mod e to the power. Okay. This you keep as it is. This I keep as it is. So, e to the power j omega n and e to the power j and this has e to the power j k omega, e to the power j k omega, that is omega k, that is from the system transfer function. Capital H e to the power j omega is mod of h to the power j omega into e to the power j into the power the angle, and angle is k omega or omega k. So, that omega k and d omega. Okay. And this is flat, and limit actually is from this band minus omega c to omega c, but you can still keep minus pi to pi, because outside that band this is also 0, this is also 0. Okay. Signal is band limited within this, outside 0, filter also designed like this, that outside this band is 0. So, integral still you can keep from minus pi to pi, okay, because it will not change anything. It is constant A, but this DTFT, this is 0 outside the band. Okay. So, even if you do not consider from minus omega c to omega c, you go from minus pi to pi, this fellow will be 0 in that range. So, integral will not will not change. So, and this is constant A over this band, right. So, it will be your A times 1 by 2 pi minus pi to pi, okay. That is, you can even keep omega c to plus omega c here, and when you take A out, and then this integral you can again come back from minus pi to pi, because you have inside you have got x e to the power j omega, and that is 0 outside this range minus omega c to omega c. So, no point if even if I extend the integral from minus pi to pi, outside this interval minus omega c to omega c, this is 0. So, it will not cause any change in the integral, but it is e to the power j omega n plus k. So, this is the inverse transform of x n at time index n plus k. So, what will you get is this capital A times original x n plus k. Okay. So, you get back x only after a delay. Here the k is positive, but I want the filter to be causal. In that case, k must be negative. So, actually the slope should be, for all causal systems, you will see the phase always goes down like this, from minus omega to omega, or from minus pi to pi you can take. Okay. K should be negative. So, actually k is a negative number. So, in that case x n plus k means n minus something. So, filter is now output is nothing but delayed version of original input. So, it is causal also. That is why for all causal systems phase is actually having downward slope, not upward slope. But what we are getting is output is nothing but input, just amplified or attenuated by a constant factor A. A could be chosen in the filter to be 1, in that case no change in amplitude, and it delayed by some constant amount. The k is known to me because I designed the filter. So, I know what is k. So, if I know x n plus k, say k is suppose minus 2. So, I know what is minus 2 value of k. So, it will be a into x n minus 2. I also know a. So, from a into x n minus 2, I can easily find out what is x n n minus 2 and all that. Okay. Because I will get the entire sequence, it will be just shifted version of the original by 2. Original sequence and the input, output will be shifted by 2 if k is minus 2, and amplified by or attenuated by A. A is known. So, I can get back by original, right. That means, if phase is linear, okay, and for causality the constant k in the phase, linear phase, the constant factor, proportionality factor should be negative. So, under that case the filter will be able to reconstruct the input x n perfectly, okay, just but for a delay and an amplitude factor. Amplitude factor is coming from the magnitude response, which is in my hand. So, I know what is A, and delay is also in my hand because it is coming from the phase is linear, k is that constant, linearity constant. Okay. Now, how to construct such filters, which will guarantee that phase is linear. Magnitude may not be fully flat, maybe little wavy type and all that is okay, maybe like this, something like this, may not be fully constant, but which is okay, but phase is linear. We will show one technique, and that is only applicable for FIR filter. In fact, only FIR filters can be made to be linear phase. No IIR filter till date, have been able to be made linear phase. That is, we say that when it is IIR filter, as of now, as of today, there is no technique by which you can design IIR filters that are linear phase. But for FIR filters, you can impose some condition on the FIR filter coefficients, and by that you can make sure that the filter phase response is linear in omega. Okay. So, our consideration now, our next topic will be linear phase filters, which are actually FIR filters. Okay. So, linear phase filters, FIR only. IIR filters cannot be made to be, we cannot give any guarantee that IIR filters will be, giving linear phase response. But if IIR filters, yes, we can make sure in our design process, we can impose some condition on the filter coefficients, which will guarantee that phase is linear. So, we will consider a filter length n, H n, filter impulse response length n. That is, we have got H 0, H 1 dot up to H n minus 1. So, we are considering an FIR filter whose impulse response is H 0, H 1 up to H n minus 1. So, total number of coefficients is capital N, length capital N, length capital N, all right. Two cases are possible, length capital N positive, length capital N odd or capital N even. Okay. Suppose we consider case A, n odd. Then what happens is this, we have got H 0 and H n minus 1, H 1, H n minus 2, or maybe okay, let me see how to explain this. total we have got n coefficients, right, n is odd. So, suppose I take 1 out, then n minus 1 that is even, and n minus by 2 then that means it is integer. So, what happens, there is a central guy and to the left I have got n minus 1 by 2 terms, to the right I have got n minus 1 by 2 terms and this guy. So, n minus 1 by 2, n minus 1 by 2. So, total is n minus 1 plus 1. So, total n. So, when n is odd, we have got a midpoint, we have got a term at the center and to the left I have got n minus 1 by 2 terms, to the right we have got n minus 1 by 2 terms. Okay. Like suppose n is say 7, then I have got H 0, H 1, sorry, let me start from there, H 0, H 1, H 2, H 3, H 4, H 5, H 6, 0 to 6 that is 7. And you see 7 means if you take one guy out, 7 minus 1 6, 6 by 2 3. So, you take 3 on this side, 3 on this side and this is the center guy. So, I arrange the coefficients like this H 0, H 1, question is what will be this guy 0 1 total n minus 1 by 2. So, it will be a dot 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 H n minus 1 by 2 minus 1, is not it, 0 1 2 dot dot dot, total will be how many terms, n minus 1 by 2 terms. So, if you start from 0 and counting 0 1 2, so it will be n minus 1 by 2 minus 1. So, if you have n minus 1 by 2 minus 1, this is n minus 3 by 2. So, it is 8 n minus 3 by 2. Then what is this guy? This guy is H, next guy. So, n minus 1 by 2. Okay, if you add 1 to it, you get back n minus 1 by 2. And then here again you have got next term. So, you add 1 to this, n plus 1 by 2. Okay, all are increasing by 1, 0, 1, 2, 3. So, n minus 3 by 2 plus 1. So, n minus 1 by 2, that was this guy. This index plus 1, so n plus 1 by 2 is this guy, dot 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 up to h n minus 2, h n minus 1. So, I am just doing nothing, I am just writing the all the terms in this manner, but I am identifying the central guy separately and this one set of points, one set of coefficients, total n minus 1 by 2 number in number on one side, another n minus 1 by 2 coefficient on the right hand side. Now, for linear phase, we will impose something called mirror image symmetry. That is, we will assume that there is at least we will assume that as though there is a mirror here. So, mirror here means this guy, their equidistance. So, they will be same. There is H 0 is same as okay. Then H 1 is same as H n minus 2 dot dot dot. If you take a general case H r, it will be see 0 n minus 1, 0 n minus 1. If you go 1 n minus 1 2, if you go up to H r, it will be n minus r, 0 n minus 1, okay, 1 n minus 2 or n minus r minus 1. So, n minus 1 0 n minus 1 minus 0, 1 n minus 1 minus 1, that is n minus 2, 2 it will be h n minus 3, that is n minus 1 minus 2 or n minus 1 minus r. Okay. So, these two they will be same. This is the condition we are imposing and the central guy will be as it is. So, dot 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 h, these two will be same, h n minus 3 by 2 is same as h this guy n plus 1 by 2. This is the thing I am imposing and the central fellow will be a independent guy n minus by 2. Okay, so this is same as this is same as this is same as this is same as this, and this. This is a mirror image symmetry condition I am imposing on the filter coefficients. That is, filter coefficients are designed from frequency space point of view, but under this condition that these coefficients I am taking to be same. Okay. If so, then what happens to the filter transfer function h e to the power j omega? We will see its phase will turn out to be linear in omega. How? We will see this now. So, actually then we have got h 0, when you take dTft, you will have h 0 plus h 1 e to the power minus j omega dot 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 h r e to the power minus j omega dot 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 up to this, right. So, in this total dTft summation, you have got one see h 0 plus h 1 e to the power minus j omega dot 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 h r e to the power minus j omega r plus dot 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 plus h this term e to the power minus j omega this n minus 3 by 2 up to this. Then you have got this middle fellow, and then you have got counterpart of this which are same, that is n plus 1 by 2 e to the power minus j omega plus dot 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 counterpart of this, it was h r, it was h n minus 1 minus r. Dot dot dot, finally the last term right. I am writing in a fully expanded form the dTft. And now you see these two terms are same by my imposition, h 0 is h n minus 1, then this term I have not drawn written it here, I could have written h n minus 2 . So, these two terms are same, h r n minus r 1 minus r, this guy, okay. These coefficients are same because of this mirror image symmetry condition I have imposed, h 0 is same as h n minus 1. So, h 0 h n minus 1 they are same, I can write it as h 0 only, h 1 is h n minus 2. So, h 1 h n minus 2, this I can write as h 1 only, h r is same as h n minus r minus 1. So, h r h n minus r minus 1. So, I can write this also as h r dot 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 dot. So, that means the summation this can be taken as common, h 0 and h 0 here, h 1 here, h r again h r here, because they are same. So, I take that common, and therefore, the summation will become, consider the general case h r and this, and the singleton fellow I write first separately out, this independent guy, this I write separately out. Okay. And then I take add them, I take h 0 common, h 1 common, h r h n minus 1 are common. So, general term I consider h r I take common. So, it is e to the power minus j omega r here, and it is e to the power minus j omega n minus 1 minus r. Not so, r is 0 1 r up to this. So, r is 0 up to n minus 3 by 2. Okay, r 0 this case, these two are common. So, you have got e to the power j omega 0 is 1. So, 1 coming from here, and r 0 e to the power minus j omega n minus 1 coming from here, like that, the general case. This is the situation. Okay. Now, I will do some just simple manipulations. if I take this thing common, e to the power minus j omega, like this factor if I take common out, H r, so e to the power minus this taking out. So, I have to add e to the power plus j omega this here. So, e to the power plus j omega minus r, because it was minus j omega r. So, minus j omega r, and since I am taking these out, e to the power minus j omega n minus 1 by tau by 2 out, to cancel it you have to have e to the power plus j omega into n minus 1 by 2 there, and here already I had n minus 1, e to the power minus j omega into n minus 1, out of which e to the power minus j omega n minus 1 by 2 has gone. So, another n minus 1 by 2 is still left. So, only this will be there minus r, because e to the power minus j omega n minus 1 was present. From that I have taken out e to the power minus j omega n minus 1 by 2. So, another n minus 1 by 2 is here. And what is this? E to the power j, if you call it theta, e to the power j theta plus e to the power minus j, same theta you see. This and this, they are same. If you call this omega into this bracketed quantity equal to theta, then omega into same thing here theta. So, e to the power j theta plus e to the power minus j theta, which is twice cos theta. Okay. So, then this factor can be taken as common, this will be twice H r cosine theta, theta is omega into. Okay. So, you see this is real, okay, this is real, this is real. So, there is no phase here as such. So, this is like the magnitude, like any complex number z is r into e to the power j theta. So, it is magnitude part and e to the power j minus omega, this is the angle part. Okay. So, what is the angle? What is the phase? Phase is minus times omega. N is odd. So, odd minus 1, that is even, even by 2, this is this is integer, minus integer times omega. Minus is coming because of causality I have told you, it has to be have a negative slope. So, phase is linear, and this part is the magnitude. But there is a word of caution. This is cosine. Cosine omega into this part changes from r to r equal to 0, one value, r equal to 2, another value like that. Okay. So, this whole thing may become negative sometimes for certain value of r. Suppose if this whole thing becomes negative, then negative means there is a pi phase shift. So, definitely at that time e to the power j pi will get added and the magnitude part of that will remain here. So, then phase will no longer be linear there, because a constant thing will get added. Phase was it was coming down like this, suddenly it will get added, it will go up like this by some pi, and again it will start falling. So, it will not be linear. So, that is why we then try to design this filter coefficient such that within the pass band minus omega c to omega c, this does not change its sign, number 1, and then its value, which is say positive now, it is not changing its sign, it is not negative, it is not turning out to be negative. Its value also does not fluctuate much, it is kind of constant, like if this is your minus omega c to omega c and this is pi here and minus pi there, you design the filter so that over this band, design the filter so that over this band it does not change, okay, does not alter much. then it is linear phase. Then it is linear phase and it does not distort the input signal, because magnitude response also kind of constant, it is not undergoing any sign change within the pass band. So, if a signal of that band limited signal within this band giving confined to this band is passed through the filter, there will be no phase distortion, it will only delayed by so much n minus 1 by 2, that much delay, okay. And magnitude response also will not undergo much change, it is a kind of constant. I will design these coefficients like this, that first this whole thing does not change the sign, does not become negative within the pass band of the signal, and also its value remains kind of constant, does not change much, okay. That is part of the design of the magnitude part. So, this is possible with the Riffrayer filter only, and you get a linear phase. Next will be the case of n equal to even. Even case also can be dealt with in a similar manner. We will take it up in the next class. Thank you.